The topic today, as Bodhi just said, is seismic detailing of special and intermediate moment frames of concrete. The detailing versus design for strength is something we have discussed earlier, and I will briefly touch upon that again. Intermediate moment frames, by now you know, are required, or intermediate detailing is the minimum required if your design category is C, and special detailing is the minimum required if your design category is D. There is really no design category B in Dhaka, at least. No design category A in all of Bangladesh. If you have design category B, your moment frame can be ordinary moment frame. And then you go with the non-seismic detailing that we discussed on an earlier day. However, for ordinary moment frames assigned to design category B, ACI 31808 section 21.2 has a couple of requirements. The first is that the beam will have at least two continuous bars, top and bottom. Simple requirement, but very important requirement. So starting with design category B, a beam will have two continuous bars, top and bottom, at least two. The size is not specified. Also, if you have shorter columns and there is a height to length ratio given, then it has to be designed to fail in flexure before it can fail in shear. Essentially, that's what it boils down to. Okay. Now, I am not going to spend any more time on that. You will not deal with other than design category C and D typically. And so you will go with intermediate and special detailing. Definitely for construction in Dhaka. A special moment frame, the reinforcement looks as you see in the picture. This is the cage for an actual building. You see the amount of transverse reinforcement. That's what stands out. The ties or hoops in columns and also in beams. Okay. So this is kind of what you are dealing with, what you are looking at, and the concrete placement is always a concern. There is so much reinforcement that you have to put into the members. You still have to make sure that concrete will get in and can be consolidated. So today we have some preliminary material, then the material restrictions. Those typically apply for special moment frames. Then we will talk about detailing of beams of special moment frames, followed by detailing of beams of intermediate moment frames. Same thing with columns. We will do special moment frame columns first, then intermediate moment frame columns, and then joints the same way. Special moment frame joints, intermediate moment frame joints. Our basis is BNBC 2020, as with everything else. And I think it has been mentioned repeatedly during the concrete sessions that the basis of the concrete design provisions of BNBC 2020 is ACI 31808. Okay. Now, after 31808 until now, we have had three editions of ACI 318, 31811, 31814, 31819, which is the latest. And in every
Dr. Ghosh, you can unmute yourself now.
yeah. So in every new edition, there are changes. Many of those changes are seismic changes in what used to be chapter 21, starting with ACI 31814. That chapter is chapter 18. Anyway, the only point I'm trying to make is that although BNBC 2020 is new, the requirements in there because they're based on ACI 31808 are sometimes pretty outdated. I know I have said it before. I think this is something worth repeating. And during this segment, one time only, I have introduced a 31811 change because I think it is of particular interest to you. Other than that, I will avoid talking about the later editions. So in 31808, the seismic detailing requirements are in chapter 21. Now, very, very importantly, when you are in chapter 21, it is not that the rest of ACI 318 goes away. The rest of ACI 318 remains applicable unless something is modified specifically in chapter 21. And one such example is development of hooked bars at exterior columns. The chapter 12 requirement is modified in chapter 21. And in that case, the chapter 12 requirement doesn't apply. What applies is the chapter 21 requirement. But unless something like that has been done, and those are relatively rare, where ACI 318 requirement has been modified in chapter 21. Except in those cases, the remainder of ACI 318 remains applicable even when you are working with chapter 21. In BNBC, you know very well, this is not 17, you see, this is another instance. I don't know how many times I went through these slides. There are things I do not see until until presentation time. So in BNBC part 6, you know, is structural design. In that, chapter 8 is on detailing of reinforcement in concrete structures. The seismic detailing is in section 8.3. That is the equivalent of chapter 21. It's titled just as chapter 21 is earthquake resistant design provisions. The rest of ACI 318 is essentially chapter 6 of part 6. It is strength design of reinforced concrete structures. So that chapter 6 remains applicable unless it is modified by section 8.3. Okay, just as I said about ACI 318. This is something, to my mind, pretty important that you have to always remember. All section numbers in this presentation that are not in blue are ACI 31808 section numbers, and all blue section numbers are BNBC 2020 section numbers from part 6, chapter 8 or part 6, chapter 6. Now, this is this is something I want to make clear up front. Special moment frames of precast concrete, which is section 21.8 in ACI 31808, are outside the scope of this presentation. I will not go in there. Intermediate moment frames of precast concrete are not recognized by 318. It simply doesn't exist until now. Okay, so there is ordinary and there is special. There is no distinction between an ordinary cast in place and an ordinary precast concrete moment frame in ACI 318. And then this has come up before. I think in a question and answer session, moment frames of precast concrete are not mentioned in BNBC 2020 Part 6, Chapter 8. This came up. There was a question, and we have posted a written answer to that question on the PRP portal. Yes, precast moment frames are not mentioned. At the same time, it does not mean that you cannot do it. You should be able to do it by ACI 318 requirements if you choose to. Okay. At the same time, I will not talk about precast in this presentation. This figure you have seen at least twice. I bring it up a third time to make the points, couple of the points that I made yesterday, which is that seismic design is a two-part affair. The first part is design for strength. You calculate a design base shear V, which depends on the R factor, which in turn depends on the structural system you're utilizing for seismic resistance. So that is one part. And depending upon the R value, you will also have to detail for inelastic deformation capacity that you need to go with the strength level you have chosen. The inelastic deformation capacity comes from proper detailing of the members and the joints. So we are now in the detailing part. The whole idea behind detailing is that so if we choose this low strength level, much of the deformation suffered by the structure in the design earthquake will be inelastic deformation. There will be damage associated with it. We will not get the structure back intact at the end of the earthquake. The damage has to be repaired, but more importantly, we do not want our structure to collapse because these inelastic deformations are too large. So the inelastic deformations must be within the inelastic deformation capacity of the structure. Inelastic deformation capacity is the range of inelastic displacements over which full factor gravity loads can be sustained. So since inelastic deformability comes from proper detailing, we have detailing requirements as part of BNBC or in ACI 318. So we are now going into the detailing part. Today, I will talk about moment frames, tomorrow about shear walls. Those are the principal elements in if concrete is your material of construction. And as I mentioned, if your design category is up to B, it is ordinary detailing. Then there are only two requirements in Chapter 21. But if your design category is C or higher, then you go into intermediate or special detailing. And that is the topic that we will spend our time on today. So this is the commentary to the scope section of Chapter 21. Okay, this is very beginning, but this is commentary. Whenever you see R, that is commentary, not an ACI provision. The provisions of Chapter 21 relate detailing requirements to type of structural framing and seismic design category. Seismic design categories are adopted directly from ASCE 7 and relate to considerations of seismic hazard level, soil type, occupancy, and use. All of that has been said before, but this is stated in the commentary upfront. Now, AC7 is many times written as AC/SEI7. In case you feel confused, SEI is the Structural Engineering Institute of ASCE, and the standard is under the jurisdiction of that institute. There is a geotechnical institute and so on and so forth. So this is the Structural Engineering Institute of ASCE7 that produces the ASCE7 standard. Now, the scope section of BNBC 2020, section 8.3 says, this section contains special requirements for design and construction of reinforced concrete members of a structure for which the design forces related to earthquake motions have been determined on the basis of energy dissipation in the nonlinear range of response. Okay, so this is acknowledged upfront. This is you are being told that the requirements are based on this energy dissipation in the inelastic range. Now, this is table 12.2-1 of AC 705. On right here, I don't have the table number, either AC 7 or the BNBC table number, but you have seen this table before. The for the different structural systems that we are dealing with, the R values, omega sub 0 values, and C sub D values are given in this table, and also height limits that apply typically in the higher seismic design categories. In moment frames, we have special moment frames of concrete, intermediate moment frames of concrete, and ordinary moment frames of concrete. They can be used as moment resisting frame system, as we discussed before, or moment frames can be used as part of dual systems. Okay, so moment frames can be used in moment resisting frame systems where there are no shear walls, or they can be used in dual systems where they are in combination with shear walls. Dual systems can have special moment frames, or they can have intermediate moment frames. So this is the area of application of moment frames, and you have the parameters, seismic design parameters, R, omega sub 0, C sub D, given in table 12.2-1. Okay, now we come to the requirements of chapter 21. We do every time special detailing first, then intermediate detailing. The materials restrictions are for special detailing only, special moment frames and special shear walls. I don't know that I have explicitly said that, but that is something very important for you to understand and remember. Okay, these limitations that you are going to talk about do not apply to intermediate or ordinary moment frames. Okay, concrete, normal weight concrete, there is a minimum strength of 21 MPa, which is slightly higher than the 17, I think, which is the absolute minimum anywhere. That I don't know is anything to discuss. Concrete of that strength is not difficult to find anywhere anymore. The more important thing is ACI 318 is probably the only major code left that does not have an upper bound on the strength of normal weight concrete. Almost every other code tells you concrete cannot be any higher than so much in strength. ACI 318 does not believe in that kind of a higher limit. We have, over the editions, adjusted requirements where the properties of high strength concrete are different from those of normal strength concrete. Also, there are basically hidden requirements, hidden upper limits on the strength of concrete, as I'll point out. But there is no explicit upper limit on the strength of normal weight concrete that you can use in high seismic construction. Lightweight concrete, on the other hand, has an upper limit on strength, 35 MPa. That's because we do not have enough test results to tell us that the hysteretic behavior, the cyclic load displacement curves of lightweight concrete members would be similar to the load displacement behavior of normal weight concrete members of the same strength. So once, that limit used to be a bit lower, has been brought up in view of more test results being available. It is quite conceivable that with more test results coming, that limit will be adjusted. But now, up until now, I mean 2022, that limit has held 35 MPa. That hasn't changed even in 31819. Reinforcement, the weldable, so-called weldable steel A706 is definitely the preferred kind. That comes only in grade 420, not anymore. Now we have a 100 KSI, 80 KSI and 100 KSI, but I wouldn't go there. That is ACI 31819 stuff. When you are dealing with ACI 318, the ASTM that it references, the ASTM A706 edition that it references has only grade 60 reinforcement or grade 420 in your units. Instead of A706 reinforcement, you may use normal billet steel A615, 40 KSI or 60 KSI. 40 KSI has become pretty unavailable anyway. And in Bangladesh, most of the reinforcement, as we discussed the very first day, is BDS ISO 6935-2. -1 is plain, -2 is deformed bars. Grades 300, 350, 400, 420, or ASTM A615 grades 275. This is ACI 318. BNBC also says ASTM 615 grades 275 and 420. Okay, so whatever is allowed in 31808 is allowed in BNBC 2020. However, BNBC has added this BDS ISO 6935-2 grade such and such. There is a higher grade reinforcement available and in use in Bangladesh, but that cannot be used for members of the lateral force resisting system of a structure assigned to design category D, as we discussed at length on that first day. Okay, you can look back to that slide set or your notes. When you use A615 reinforcement or BDS 6935-2, there are supplemental requirements. There are requirements in addition to those, addition to the requirements that are in those standards. Okay, these supplemental requirements tend to be very important. So the first supplemental requirement, remember the black is ACI 31808, blue is BNBC 2020. The actual yield strength shall not exceed the specified yield strength by more than 125 Newton per square millimeter. It's 18 KSI in our units. So the actual yield strength shall not exceed the specified yield strength by more than 125 Newton per square millimeter. On retesting, you can go another 20 Newton per square millimeter, but then 145 is the limit. You cannot go beyond that. This is an extremely important requirement or limitation, because in seismic design, I will say this now, I may say it many more times later today or in the future. In seismic design, more is not always better. Quite often, it is not. And that came up with the load combinations with overstrength factor yesterday. You just cannot use it when you like and make members stronger. That may very well be to the detriment of your structure. So this is when the yield strength of your reinforcement is significantly higher than what you specified. The flexural strength of the member reinforced with that steel will be higher than you figured. That beam, stronger in flexure, will attract more shear force to itself in an earthquake. And we will not be correspondingly increasing the shear strength of the member, thereby making brittle shear failure more likely. This is why we absolutely do not want the yield strength of the reinforcement to be much higher than the specified value. This was a serious problem with structural steel. They have kind of solved it now. This is I don't know that it is a problem. We have been very mindful of this from the beginning. Okay. So once again, if the yield strength is higher than you specify, the moment strength of your member will be higher than you bargained for. That high strength member will attract more shear force to itself in an earthquake. Shear moment is, remember that the two are related. So the higher shear force will cause shear failure preceding flexural failure, because we will not be correspondingly increasing the shear strength of the member. And shear failure is brittle, comes without warning. We absolutely do not want it. Okay. So that is supplemental requirement number 1. It is in 31808. It is in BNBC 2020. Something BNBC has that ACI 318 did not have until the 2014 edition is that it basically says the elongation over an 8-inch gauge length of A615 or the BDS bar 6935-2 bars shall be the same as that of A706 bars. Okay. So I will say it again, the elongation over an 8-inch gauge length of the A615 bars or the BDS 6935-2 bars shall be the same as the elongation over an 8-inch gauge length of A706 bars. Okay, so that requirement was added to ACI 318 in 2014, but it is in BNBC 2020. The third supplemental requirement is that the actual tensile strength, when you test your reinforcing bar specimens, the actual tensile strength shall not be any lower than 125% of the actual yield strength of the reinforcement. Okay? So the actual tensile strength, the measured tensile strength, shall not be any lower than 125% of the actual yield strength. This is in order for the reinforcement to have inelastic deformation capacity. We are looking for significant capacity for the reinforcement to yield without losing strength. Okay, so if the reinforcement has inelastic deformation capacity, the structural member reinforced with that steel will also have inelastic deformation capacity. Particularly beams are totally governed in their behavior by the reinforcement, as we discussed earlier, because we design beams to be under reinforced. The concrete almost doesn't play any role. So this is why this requirement. Now the 125% differential between tensile and yield strength is something many steels cannot meet. So this requirement has also been a significant screen in many reinforcements. If you, Bangladesh, for instance, if you want to import reinforcement from somewhere else, China, Korea, you may find that the reinforcement doesn't meet this requirement, and then you cannot use it. ACI 318 said pre-stressing steel resisting earthquake-induced flexural and axial loads in frame members shall comply with 416 for strand and 722 for high-strength bars. This is not in BNBC 2020, as also came up in discussion earlier, or it is in that written reply to a question that we posted on the website. So BNBC does not officially recognize the use of pre-stressed members as part of the seismic force resisting system of a structure in a high seismic design category. It is as simple as that. Okay, so there is no standard cited for pre-stressing reinforcement in BNBC. Okay, going beyond the standards, the value of F sub YT, that is yield strength of transverse reinforcement, used to compute the amount of confinement reinforcement shall not exceed 100 KSI, 700 MPa. This is the highest allowed anywhere by 31808. Value of F sub YT, yield strength of transverse reinforcement, used to compute the amount of confinement reinforcement shall not exceed 100 KSI. Then it says the value of F sub Y or F sub YT, F sub Y for longitudinal reinforcement, F sub YT for transverse reinforcement, used in design of shear reinforcement. So transverse reinforcement in a beam or a column has dual purpose. It confines the concrete. It also carries shear for you. As long as you are dealing with the confining role of the transverse reinforcement, the limit on strength is 100 KSI. However, when you are designing the same reinforcement to act as shear reinforcement, you cannot utilize more than 60 KSI yield strength. The two together tells you that the value. So this says the value of f sub y, f sub yt used in design shall conform to 1142, and 1142 says the values of f sub y and f sub yt used in design of shear reinforcement shall not exceed 60 ksi. Okay. Uh, welded wire reinforcement, you go up to 80 ksi. Anyway, I think you have to fully understand the what is being said. So transverse reinforcement, when you are designing it to confine the concrete, your strength limit is 100 ksi. And this is very, very important, as I'll explain next. Extremely important. It took a lot of work to get this 100 ksi approved as early as 3/1808. Now it's a different story, but back then it was a huge struggle, and we went through all the trouble because it is important. But when the same reinforcement acts as shear reinforcement, we should not count on yield strength beyond 60 ksi, because if we do, we will be looking at wide shear cracking in our beams, and that is very objectionable. So in the shear carrying role of the transverse reinforcement, your limit is 60 ksi, 420 MPa. Now, why is the 100 ksi limit for confinement reinforcement so important? So to explain, I brought up the requirements for special reinforced concrete columns, which we will discuss later on in the presentation. When we detail a special reinforced concrete column, we consider a region of potential plastic hinging at each end, the length of which is specified in the code. Within that region, we have to have closely spaced closed hoops at a maximum spacing given here. 1/4 of the smaller planned dimension of the column, 6 times the longitudinal bar diameter, or this S sub x, which varies between 4 and 6 inches. Okay, that will come up later. I don't think I put it in here. When we go to column detailing, you will see that. So to cut a long story short, that maximum spacing usually is about 4 inches, 100 millimeters, which is tight, quite tight. Now, to make things worse, this transverse reinforcement, these hoops, must have total cross-sectional area of the legs in each orthogonal direction. The sum of the cross-sectional areas of those 3 legs, as well as the sum of the cross-sectional areas of this leg, and that leg, must be equal to the area given by those 2 formulas, and the larger amount governs. So the minimum cross-sectional area of the transverse reinforcement must be no less than the larger value given by those 2 formulas. 4-inch hoop spacing, tight as it is superseded by this requirement. The cross-sectional area requirement is so high that for the normal bar sizes that we use, 4-inch maximum spacing is not sufficient. We normally end up with 3 inch or 2.5 inches. Okay, 3 inches, 75 millimeters, 2.5 would be, I don't know, 60, something like that. Now, the thing is, this is very, very important. The cross-sectional area required by both formulas is proportional to the concrete strength, F sub C prime. So as we go from 4 KSI to 6 KSI to 8 KSI concrete, the required cross-sectional area of transverse reinforcement increases. Okay, so that means that for the same bar size, the spacing has to be tighter and tighter. And when we end up with 1.5 inch or 1 inch spacing, concrete cannot be placed anymore. So that is a hidden limit on the strength of concrete that we can use in columns in high seismic areas. Yes, ACI does not have a formal upper limit on the strength of normal weight concrete, but here there is a hidden limit. Okay? The only way to get around this is if, as F sub C prime increases, we can also increase F sub YT, the yield strength of the transverse reinforcement. This is why 100 KSI limit on transverse reinforcement is so important. Okay, that allows us to use high strength concrete in columns, which is quite often highly desirable. It gives us smaller columns, frees up rentable space. Anyway, high strength concrete and high strength reinforcement go hand in hand. Okay, you cannot utilize one without the other. So and let me show you in graphic terms. So with this is a cage for an actual building. This is Gary Kupczynski's office in Seattle. Gary gave me the slide. The left-hand cage is with 60 KSI reinforcement, and you see the spacings. The right-hand cage is, I don't remember now, it was 75 or 80. It was not super high strength, 100 KSI. Look at the difference in the two cages. Okay, so there is a whole lot to be gained by using high strength transverse reinforcement in terms of the placeability of the concrete, the behavior of the member, and so forth. So anyway, I wish, I hope that you understand the importance of that, I would say, relaxation that was introduced in 1808. Okay, welding of stirrups, ties, inserts, or other similar elements to longitudinal reinforcement that is required by design shall not be permitted. Okay, this is a very important requirement in high seismic construction. Welding of stirrups, ties, inserts, other similar elements to longitudinal reinforcement that is required by design. So if you need to weld a tie to a longitudinal bar, it has to be a construction bar added for that purpose. It cannot be a bar that carries stresses by your design. Okay? So BNBC has a little more. Reinforcement required by factor load combinations, which include earthquake effect, shall not be welded except as specified in section such and such. Okay, that's kind of a blanket restriction. In addition, the ACI language, welding shall not be permitted on stirrups, ties, inserts, or other similar elements to longitudinal reinforcement required by design. Okay, so pretty severe restrictions on welding in high seismic construction. Okay, we now will talk about detailing of beams of special moment frames. in this section, followed by beams of intermediate moment trends. Okay. The first question is, what is a beam and what is a column? In the main body of ACI, there isn't a formal distinction because it really does not matter a whole lot. It is up to the engineer to decide. Decide. Typically, vertical members are columns or designed as columns. Horizontal members are designed as beams. If it is an inclined member, that's where judgment comes in, and uh, it doesn't matter a whole lot in non-seismic construction whether you consider something a beam or a column. Seismic construction, high seismic construction, it makes a huge difference because the detailing requirements are very different for beams and columns. Okay, so we need to make a formal distinction. And the distinction that ACI 318 has drawn pretty arbitrarily is that if a member is subject to factored axial compressive force larger than 1/10 A sub F sub C prime A sub G, gross cross-sectional area multiplied by the specified compressive strength, then it is a column. As long as the factored axial force is less than or equal to 1/10 of A sub G F sub C prime, it is a beam. Okay. So factored axial force, now that includes earthquake effect. If earthquake causes axial force, which typically does not in a beam, but in principle, the axial force due to earthquake is included in a column. That is kind of important. So factored axial compressive force less than or equal to 1/10 of S sub G F sub C prime. Clear span larger than or equal to 4 times effective depth. The so-called slenderness ratio, whatever it is called, the span to depth ratio shall be larger than or equal to 4. So that means deep beams cannot be part of the seismic force resisting system in design category D. Okay, so span to depth ratio at least 4, clear span to effective depth. Width to depth ratio 0.3. So if you have a 30-inch deep beam, the width has to be at least 9 inches. Okay. So that's easy to follow. Okay, width to depth ratio is larger than or equal to 0.3. So you cannot have very narrow beams. That's what it means. And then the width, not the depth, the width has to be larger than or equal to 250 millimeters, 10 inches. It also has to be larger than or equal to 10 inches and has to be less than or equal to something. And that part I will explain. Now, so two things are being done here. One is a distinction is being drawn between a beam and a column. So we are saying that the detailing requirements in this section 21.5 apply to members with factored axial force less than or equal to A sub G F sub C prime over 10. And then we are imposing some dimensional limitations. Okay. Those dimensional limitations are being imposed because although there have been a lot of beam tests under simulated seismic loading until now, all those tests are within certain dimensional ranges. If we stray far beyond that range, we are in uncharted territory. We do not know if our beams will behave properly when an earthquake comes. So this is why these dimensional limitations are kind of important. Okay, so the width cannot be any smaller than 10 inches and has to be no larger than something. Okay, let's that language is not easy to follow without this figure. Okay, so the subject here is when the beam framing in when a beam framing into a column is much wider than the column, as shown in this picture. Okay, this is the cross section. This is the plane of the same thing. The beam is significantly wider than the column. And the question is, how wide can the beam be and still eligible to be part of the seismic force resisting system of a category D structure? Okay. Obviously, if it is too wide, then it will not, the whole width of the beam will not act together with the I'm not, the whole width of a very wide beam will simply not be effective. Okay? The whole width will not bend together. So so there needs to be some kind of limitation. Now, in this picture, the up and down direction is the direction of analysis. That is very important to understand. Okay, the column has dimension C sub it. The column dimension in the direction of analysis is always C sub 1. The perpendicular direction is C sub 2. Yeah. And then we cut this section AA. You see the section here. This is the this is the C sub 2 dimension. Okay, and the C sub 1 dimension is into the screen. I hope you're with me. Okay, this is, if you cut a section here, this is C sub 2, this is C sub 2, and the C sub 1 dimension is into the screen. Now, the ACI limitation is saying that this overhanging flange width, this width, cannot be any greater than the smaller of two things, the C sub 2 or 75% of the dimension into the screen, 75% of C sub 1. So this overhang cannot be any greater than the smaller of two things, C sub 2, this column dimension, or 75% of C sub 1. So that's how wide the beam can be and still serve as part of the seismic force resisting system. Okay, what this picture shows is what was said here. Now, this is a very important point. The next thing that I'm going to say, flat plate column frames where there are no beams, the slab itself acts as beam. We can come up with an effective slab width to describe, may not be the best word, to define. We can come up with an effective beam width that defines the part of the slab that acts as a beam. But that effective beam width will be wider than what is being allowed by this restriction. So we do not have detailing requirements for that effective beam width. And this is why we cannot make flat plate column frames part of the seismic force resisting system in seismic design categories D, E, and F. ACI 318 has no explicit restriction. It never says in black and white, flat plate column frames cannot be part of the resisting system of a structure assigned to design category D, E, or F. BNBC has added that kind of a statement, which I like very much. But ACI 318 does not allow flat plate column frames as part of the resisting system because of this dimensional limitation. I want to point that out to you. This is very important. Okay. So this is the BNBC statement. The provisions of special moment frame shall not permit the use of slab without beam as part of seismic force resisting system. I think this is wonderful that this is explicitly said in the code. Okay. Longitudinal reinforcement in a special moment frame beam. A number of significant requirements. Minimum 2 bars continuous top and bottom. The maximum percentage of reinforcement top as well as bottom, 2.5%. This is 3/4 of row balanced or its equivalent in the main body of the code. The net tensile strength shall not be any lower than 0.004. Remember, in high seismic construction, the 2.5% limit is a constructability limit. Above that, concrete placement becomes difficult. That is the reason. The minimum reinforcement ratio, top as well as bottom, is either 140 over f sub y or 0.25 square root of f sub c prime over f sub y, whichever is the smaller of the two. Okay, so there is a minimum limitation, there is a maximum limitation, and 2 bars continuous top and bottom. Then if you have, let us say, six, our number 8, 25 millimeter bars at the top at the support section. You must have at least 3 25 millimeter bars at the bottom. The positive moment strength shall be no lower than half the negative moment strength at the support section. I'll say it again. The positive moment strength shall not be any lower than 1/2 of the negative moment strength at the support section. This is extremely important. Gravity thinking engineers have a lot of problem with this, but this is necessary in seismic construction. The gravity loads always cause negative bending moment at the support section, which requires top reinforcement. Everybody understands that. Earthquakes can cause negative bending moment, which would be additive to the gravity moment, or they can cause positive bending moment when the earthquake reverses direction. The positive bending moment under strong earthquake excitation could be larger than the negative bending moment due to gravity. And then we would end up with net positive moment at the support section requiring bottom reinforcement. Okay, this is fundamental, this is important, but after every earthquake we see bottom cracks at supports because gravity thinking engineers simply would not provide that bottom reinforcement, which is easy to do. So this is a very, very important requirement. And then nowhere along the span of the beam can we have either positive moment strength or negative moment strength that is smaller than 1/4 of the larger amount of negative reinforcement provided at the two support sections. This is, I said quite a bit. I think it is difficult to follow. So So the negative, this support section has a negative moment strength. That support section has a negative moment strength. The larger of the two, okay, is a number. 1/4 of that has to be at least the positive or the negative moment strength everywhere along the length of the beam. But let me tell you in terms of, so let us say we have 8 number 8 bars here and 7 number 8 bars here. Larger of the two is 8 number 8. 1/4 of that is 2 number 8. 2 number 8 bars have to be continuous through the top and the bottom of the beam. Okay, so nowhere along the span can the positive or the negative moment strength be any lower than 1/4 of the larger moment strength at the two support sections. Okay, so very significant requirements. Then transverse reinforcement, special moment frame beams. We consider a region of potential plastic hinging at each end. The length of that region is twice the overall depth of the beam. If the depth is 2 feet, the width of that, the length of that critical, the length of that potential plastic hinge region is 4 feet. Within that region, we have to have closely spaced closed hoops. The word hoop is important. I used it before. I didn't say anything. Hoop is a closed piece of transverse reinforcement. Keep that in mind, and I will elaborate on that. Okay, so closely spaced closed hoops. Spacing not to exceed any of those 4 quantities. 1/4 of the effective depth, 8 times the smallest longitudinal bar diameter, 24 times hoop diameter, or 12 inches. Okay, so the spacing cannot exceed the smallest of those 4 things. At the end of the plastic hinge region, we have to have stirrups at a spacing not to exceed 1/2 of the effective depth. These can be stirrups. They don't have to be hoops. They don't have to be closed. Okay, and then if we have lapped, if we have installed, if we have lap splices of the longitudinal reinforcement, doesn't matter top or bottom, we have to have the lap confined by transverse reinforcement at a spacing not to exceed 1/4 of the effective depth or 100 millimeters, whichever is the smaller of the two. Okay, 1/4 of the effective depth or 4 inches, whichever is the smaller of the two. So in the plastic hinge region, hoops at a spacing not to exceed the least of 4 things. Then open stirrups at a spacing not to exceed d/2, and then over the splices, the hoops at a spacing not to exceed 1/4 of the effective depth of 4 inches, whichever is the smaller. The hoops can be one-piece affairs like this, where that hook has to be, both hooks have to be seismic hooks. Remember, 6 bar diameter extension subject to a minimum of 3 inches. These are not easy to manufacture. More than the manufacturing, the placement is rather difficult. So ACI 318 has for a long time allowed 2-piece hoops, where we have a stirrup that has seismic hook at each end, and that is closed by something called a cross tie, which has a seismic hook at each end and a standard hook at the other end, 90 degree with 6 bar diameter extension. Okay. Now, the seismic hook and the standard hook has to alternate. On the next hook, the 90-degree bend will go to the left face, the 135-degree will come to the right face. Unless a beam, not a beam, a slab frames into the beam only on the right face, in which case all the 90s will be on the confined right face and all the 135s will be on the unconfined left face. We go into that level of detail when it comes to seismic detailing. Okay. Now there are also overlapping hooks that are used. Uh, I, uh, I, well, I wouldn't say fairly often, but they're used. Okay. So hoops and overlapping hoops. Now this is the only time I brought in ACI 31811. This spacing, which used to be the smallest of four things, remember, d over 4, 6 times the smallest longitudinal bar diameter. It used to be 24 times the tie diameter, that is gone, and the 12 inches, it was 300 millimeters. 300 millimeters is now 6 inches. Okay, so that was an ACI 318 change. Very, very important change. The spacing of these hoops in the plastic hinge region was made significantly tighter. This was done on the basis of tests at the University of California, Berkeley. You see the kind of test that was done. And this is the comparison of the hysteretic curves of a beam that was detailed by ACI 31808, and red is beam detailed by the altered ACI 31811 requirement. And you see that the ACI 318 detailing gives you better performance, gives you fatter hysteretic loops and so forth. So that kind of justified the change, or the change was made based on the testing. Okay, uh, where hoops are required, the plastic hinge region, primary flexural reinforcing bars closest to the tension and compression faces shall have lateral support conforming to what is required for columns, essentially. Okay, the chapter 7, non-seismic detailing, I explained this to you, or let me show you. So when we talked about non-seismic detailing, I mentioned that in columns, every other bar has to be laterally supported by a corner of a tie or a cross tie, and the maximum spacing center to center between any two the maximum spacing center to center between, not center to center, the maximum clear spacing between a supported bar and an unsupported bar cannot exceed 6 inches. Okay, so that's what this is referring to. We are talking about beams, but we are saying where hoops are required, primary flexural reinforcing bars closest to the tension and compression faces shall have lateral support conforming to those rules. So in other words, the longitudinal bars in the plastic hinge region of a beam shall be confined like column bars. That's precisely what that is saying. The spacing of transversely supported flexural reinforcing bars shall not exceed 350 millimeter. This is not in chapter 7. So the spacing between any two supported bars shall not exceed 14 inches. That is being said specifically here. Skin reinforcement is not subject to the lateral support requirement. Now, I said only the first sentence is explicit in BNBC 2020. The rest of it is not explicitly stated. But this is kind of important. I would say it again. The beam bars in the plastic hinge region must be confined like column bars. Okay, shear design of special moment frame beams, extremely important. So, beams of special moment frames are not designed for the shear that our analysis of the structure under code prescribed seismic forces tell us develop in the beam. We do not design a special moment frame beam for the shear that our analysis says develops in the beam. We design a special moment frame beam for the largest shear that can develop in the beam. Okay, so in order to calculate that, if we are figuring out the largest shear at this support section, we will consider the largest bending moment that can develop at that support section in that direction, the clockwise. We will consider the largest bending moment that can develop in the opposite direction. So if this is a negative moment, we will consider the largest negative moment that can develop at this support section. We will consider the largest positive bending moment that can develop at the opposite support section. We will add the two moments together, divide by the clear span. That will give us the largest shear here. And on top of that, we will add the shear caused by gravity sitting on the beam. Okay, the gravity sitting on the beam would be 1.2 dead plus 0.5 live. It is not 1.6 dead plus it is not the gravity combination, it's the gravity part of the seismic additive seismic load combination. That's kind of important. So this gravity is 1.2 dead plus 0.5 live. Now the largest bending moment that can develop at a section, we have a name for it. We call it probable moment strength. So there are three different flexural strengths in ACI 318. There is the nominal flexural strength, which we have talked about, calculated using nominal member dimensions, nominal reinforcement, whatever we designed for. And very importantly, assuming that the tension reinforcement yields, the tensile reinforcement stress is equal to yield strength. That is nominal strength, M sub n. In flexural design, we do not count on the entire nominal strength. We discount it by a strength reduction factor phi. Phi times M sub n is called design flexural strength. Okay, so in flexural design, we use design flexural strength, phi times M sub n, because that is the conservative thing to do. Shear design is the other way around. We need to use an upper bound value of M sub n, not M sub n, the largest moment that can develop. Okay, so we don't want to go below M sub n. We need to go above M sub n. We want a reasonably overestimated flexural strength, and that is M sub PR, probable flexural strength. The difference between M sub n and M sub PR is M sub PR is calculated using steel stress equal to 125% of the yield strength. Okay, not 100%, as in the case of M sub n. So the shear calculated on the basis of M sub PR at the two ends is what we designed for, and that makes shear failure preceding flexural failure extremely unlikely. Okay, intermediate moment frame beams. The top as well as the bottom reinforcement. Here, the 21.3 section does not say two continuous bars top and bottom, but I will show you that that is required by section 21.2, which applies to design category B and higher. So two continuous bars top and bottom remain. The minimum is the same as for special moment frames, but the maximum has gone back to non-seismic construction. It's not 2.5% anymore. All we are saying is net tensile strength shall not be any smaller than 0.004. Okay. Then the positive moment strength at a support section shall be no less than 1/3 of the negative moment strength. It was 1/2 in the case of special moment frames. Now it is 1/3. Okay. And nowhere along the length of the beam shall the positive or the negative moment strength be any smaller than 1/5 of the larger negative moment strength at the two support sections. Okay, so if we have 10 number 8 bars here, 8 number 8 bars here, the larger would be 10 number 8 bars. 1/5 of that would be 2 number 8. The 2 number 8 have to be continuous top and bottom. Now I brought up or decided to include chapter 12, which is development length section, chapter of the code, and 21.2, which applies to ordinary moment frames assigned to design category B. Okay. These requirements, chapter 12 requirements, remain applicable, and what you will do for design category B, you will also do for design category C. So beams, so together, this is the requirement. Beams shall have at least 2 continuous bars at both top and bottom faces. That applies to intermediate moment frame beams. Continuous bottom bars shall have area not less than 1/4 the maximum area of bottom bars along the span. So whatever you need in the span section, 1/4 of that reinforcement has to be continuous. That is a basic chapter 12 requirement that does not go away. So I just wanted to point that out, that the basic requirements remain in force. Transverse reinforcement intermediate moment frame. We consider the intermediate moment frame beam. We consider the same region of potential plastic hinging at each end, twice the overall depth of the beam. Within that, we now require, when I say now, 31808 required it, I don't remember which edition, but before a certain edition, those could be stirrups. That was changed. So we have now, for quite some time now, we require hoops within the potential plastic hinge region of intermediate moment frame beams as well. Okay, the maximum spacing is what used to be the maximum spacing for special moment frame beams. Or if you are going by 31808, this spacing limitation is the same as for special moment frame beams. No difference. 1/4 of the effective depth, 8 times the smallest bar diameter, 24 times hoop diameter, 12 inches. Okay. So outside of the plastic hinge region, we can have stirrups at a spacing not to exceed 1/2 of the effective depth. So there isn't a whole lot of difference between the special moment frame beam and the intermediate moment frame beam when it comes to transverse reinforcement in SCI 31808. Okay. The that spacing has become much tighter for special moment frames, as I pointed out in ACI 31811. The sheer design of intermediate moment frames. Uh, there are two ways you can go. You can approach it like the sheer design of special moment frame beams, except if it is an intermediate moment frame beam, you will calculate the maximum shear that can develop by considering nominal rather than probable moment strength at each end. Okay, so the shear calculation shall be based on moments equal to the nominal moment strength acting at the two ends of the beam. It's probable moment strength in the case of special moment frame beams, nominal moment strength in the case of intermediate moment frame beams. That is one choice for intermediate moment frames. Special moment frame, you don't have a second choice, but for intermediate moment frames, we have another way we are allowed to go. If we don't want to calculate shear based on nominal moment strengths, what we can do is go by item B, which says the maximum shear obtained from designed load combinations that include E, with E assumed to be a multiplier times, well, I think the language is. So we have two seismic load combinations. Remember, this is the additive, there is a counteractive load combination. The maximum shear will come from the additive load combination. So the counteractive is not in the picture. Now, in the case of beams, what we can do in shear design is to design the beam for twice the shear, twice the earthquake shear that our analysis says develops in the beam. So E is the earthquake induced shear. Remember, the E is the sum of E sub H and E sub B, horizontal earthquake effect, vertical, all of that is understood. Anyway, E is the earthquake induced shear as obtained from analysis of the structure under code prescribed seismic forces. If our analysis says 100 kips of shear develop at a section, we design for 200 kips plus whatever shear is caused by gravity loads. Okay? So in this load combination, if we are designing an intermediate moment frame beam for shear, we could simply double the earthquake shear and not worry about calculating shear, maximum shear based on nominal moment strengths at each end. If we are designing a column of an intermediate moment frame, which we will discuss later, the earthquake-induced shear has to be multiplied by omega sub 0. 2 is not sufficient. Omega sub 0 for intermediate moment frames is 3. So we will multiply the earthquake-induced shear by a factor of 3. Okay, now, yeah, I probably am running behind, which I didn't expect today. Anyway, let's take our break. It's 29, so I'll come back at 34 after, and we will start from here. Okay. Okay, the 5 minutes are up, so let us start again. We are now beginning to talk about slab column, flat plate column frames being utilized as intermediate moment frames. They cannot be special moment frames, but they can definitely be intermediate moment frames. When you want to do that, utilize a flat plate column frame as an intermediate moment frame. At every critical section, you will design for the combined bending moment coming from the gravity loads and the earthquake effects. Okay. So if it is not part, if it is, if the slab system is designed for gravity only, the earthquake effects are obviously not in the picture. However, if you are designing a flat plate column to be an intermediate moment frame, the moments caused by the seismic forces, the equivalent static seismic forces, have to be added to the bending moments caused by the gravity loads. Okay. I have shown you this picture probably multiple times. the gravity moments cause this kind, the gravity loads cause this type of a moment distribution. The lateral loads due to earthquakes cause this type of a moment distribution. When you combine, you will have very significant moment transfer, unbalanced moment transfer at every support section, because the unbalanced moment due to the lateral loads are the sum of the moments to one side of the support and the moment on the other side of the support. Okay. So we are looking at significant, when we utilize a flat plate column frame as an intermediate moment frame, we are looking at significant moment transfer at every support section. Now these discussions are all fresh, so I can go a little faster. So you remember that a fraction of the unbalanced moment is transferred by flexure, the remainder by shear. Gamma sub F is the fraction that is transferred by flexure and is typically around 60%. The reinforcement needed to resist the part of the unbalanced moment that is transferred by flexure has to be placed within a narrow moment transfer band running along the column lines. All this discussion must be quite fresh in your mind. Okay. So gamma sub F times the unbalanced moment is transferred by flexure. 1 minus gamma sub F times the unbalanced moment is transferred by shear. Gamma sub is F is 60% for square columns, and the reinforcement that we need to resist this 60% of unbalanced moment by flexure has to be placed within a narrow moment transfer band, the width of which is the transverse column dimension C sub 2 plus 1.5 times the thickness, the slab thickness on either side. Okay. The detail that I don't think I have brought up before, and this is only for intermediate moment frames. This is chapter 21 requirement. If when you have this situation, the column sticking out of the edge of the slab, okay, this dimension C sub t from here to there, okay, from the end of the column to the end of the slab. The C sub t dimension, the 1.5 times h on either side shall not exceed C sub t. That is the stipulation that has been made in recent editions of ACI 3 or going quite a while back. So the width of the moment transfer band is the C sub 2 plus 1.5 times slab thickness on either side, as I have been saying all along. What I'm adding is that 1.5 times h cannot exceed C sub t, where C sub t is the distance from the column face to the edge of the slab in cases where I don't have to say in cases where, even where the column goes beyond the edge of the slab. Anyway, C sub t is pretty graphically shown here. Now, if it is an edge column, then it is not 1.5 times h on either side. It is on one side only. Okay, so the effective width of the slab for an edge column is illustrated in this picture. I don't think I can improve on this very graphic picture. Now, for intermediate moment frames, in addition to saying that you shall place reinforcement needed to carry gamma sub F times the unbalanced moment within this narrow moment transfer band, we are saying that at least half the column strip reinforcement must be placed within that narrow moment transfer band. This is an explicit requirement for intermediate moment frames. Yes, you shall, as in gravity frames, place the reinforcement that you need to resist the part of the unbalanced moment that is transferred by flexure within the narrow moment transfer band. But here we are saying if it is an intermediate moment frame, you shall place at least half the column strip reinforcement within the moment transfer band. Okay. So this is an additional requirement. This M unbalanced moment has been variously denoted by M sub U. Here it is M unbalanced UNBAL. In more recent editions of ACI 318, it is called M slab, M sub slab. I didn't try to be consistent because that would have been pretty tough. Okay, so the what I just said is at least one half of the column strip reinforcement shall be placed within the narrow moment transfer band. Okay. Additional detailing requirements. We are talking about intermediate moment frames consisting of flat plates and columns. Okay. So this is the column strip of the slab. So not less than 1/4 of the top reinforcement at the support must be continuous. And when we say at the support, it is the larger amount at the two supports. Not less than 1/4 of the top reinforcement at the support must be continuous through the top. Not less than 1/3 of the top reinforcement at the support. That is not span moment. This is exactly what is written. Not less than 1/3 of the top reinforcement at the support shall be continuous through the bottom of the column strip. Okay, top and bottom reinforcement must be fully developed at the support faces. For the middle strip of the slab, the only requirement is not less than 1/2 of the bottom reinforcement and midspan must be continuous through the supports or anchored at the support. Okay, so these are not very onerous requirements, but these are important requirements that you have to be aware of. This is for slab column frames that are serving as intermediate moment frames. The punching shear part is significantly more important, as I have kept on telling you. So slab column frames are susceptible to punching shear failure during earthquakes if the shear stresses due to gravity loads are high. That is, I think, intuitively understandable. If shear stresses due to gravity loads are high, those are taking up much of the shear carrying capacity of the slab, and then you don't have room for additional punching shear caused by moment transfer, which should come from earthquakes. Okay, so slab column frames are susceptible to punching shear failure during earthquakes if the shear stresses due to gravity loads are high. Okay, so because of that, this is something extremely important. At the critical sections for columns, the critical section for two-way shear that you are by now totally familiar with. At the critical section, two-way shear caused by factored gravity loads shall not exceed 40% of phi times V sub c. V sub c we have looked at, and I have slides that repeat the V sub c information. But you understand what I'm talking about. This came up once in earlier discussion. The days are now mixed up. Okay, so if If a flat plate is serving as part of an intermediate moment frame, then at the critical section around a column, you cannot have punching shear due to gravity exceeding 40% of the punching shear that concrete alone can carry. That will leave ample room for additional punching shear caused by moment transfer. Okay, I think that should be pretty clear. Phi is 0.75. V sub C is given by three different formulas, and the smallest one governs. Okay, now this is a very, very severe requirement. If we had to live by this, most people wouldn't build flat plates in design category C. It would be economically infeasible. So there is a waiver. It shall be permitted to waive this requirement. You don't have to live with this limitation of 40% phi times V sub C if the slab design satisfies 21.13.6. Very, very important section. So we have a severe limit on punching shear caused by gravity, 40% phi times V sub C. At the same time, we have a waiver. You don't have to live with that limitation if you satisfy 21.13.6. Okay, this is repeat. I probably will just not spend time on. So you know about the critical section for punching shear, the three V sub C formulas, and the smallest amount governs. Okay, so all of that has been covered pretty recently. This is the section 21.13.6. Okay, I keep on saying extremely. This is about the best thing we have done for flat plates. In as long as I remember this section for slab column connections of two-way slabs without beams. Slab shear reinforcement satisfying the requirements of section such and such and providing V sub S not less than, in our units, 3.5 square root of F sub C prime B sub 0D shall extend at least 4 times the slab thickness. Okay, the details aside, the origin, let me tell you, I don't know if time is a problem yet, but anyway, this is extremely important, and let me tell you what this is. So back in, I don't know, very late in the 90s, I was at a meeting that the Structural Engineers Association of California convened of major design offices in California, 6 from Northern California, 6 from Southern California. And the SEOC wanted to find out how these offices were meeting deformation compatibility requirements for flat plate column frames, which obviously had to be combined with shear walls or brace frames in California. And to the utter surprise of SEOC and definitely my surprise, the design offices said the deformation compatibility requirements simply did not apply to slab column frames. Those were for beam column frames only. So they did not try to satisfy deformation compatibility, and the local jurisdictions, the plan check people never said anything. So together with SEOC, I worked for Port and Cement Association back then. We decided that this was an untenable situation, very unsafe. So we came up with a solution that said you shall, if you are going to not worry about deformation compatibility. Deformation compatibility between gravity frame and seismic force resisting shear walls, which you are ignoring anyway, shall be deemed to be satisfied if you throw in a prescribed amount of punching shear reinforcement at every slab column joint. Okay. So deformation compatibility, which you are not checking anyway, shall be deemed to be satisfied if you provide at every slab column joint a prescribed amount of punching shear reinforcement. This is the prescribed amount. Reinforcement capable of developing a shear of 3.5 square root of F sub C prime. But in reality, it is not at every joint. We said at joint. So I'll give you more details. But this is in principle the uh, origin of the requirement. Now this was done for flat plate column frames that are not part of the resisting system of a building in a high seismic design category. This is why the section is 21.13.6. This is not the intermediate moment frame section. Intermediate moment frame section is 21.3 or whatever it was, 21.4 in 31808. I don't 21.3. So this is a 21.13 section, gravity frame. That's where we placed it. Intermediate moment frame section is saying that if you would do what you would do for a gravity frame that is combined with shear walls in a high seismic zone, then you are good. Then you don't have to live with the 40% P times P sub C limitation. Okay, so 21.13.6 is not formulated for intermediate moment frames, but intermediate moment frames are invoking that section. If you do what we require there, you don't have to live with the severe limitation of 40% P times P sub C on the shear that develops, the punching shear due to gravity. Okay. So the prescribed amount, I don't know how important that is. The punching shear reinforcement that we are talking about can be in the form of stirrups, which require a minimum depth. You can look that up. I don't know that that is terribly important. Today, as I mentioned, the pretty much the standard punching shear reinforcement are the stud rails. That's what everybody provides. And I know plenty of California engineers who will just throw this in. They don't try to figure out if they can get exemption, this and that. This is cheap insurance. This is the cheapest insurance you can buy for a flat plate column frame in a high seismic design category. Okay, I will go as far as that. This is to be as I said, 21.13.6 is the best thing we did for flat plates in a maybe forever. Anyway, so let me. This requirement is saying let me try to explain with this picture. This is commentary to section 21.13.6. This figure is in there. Okay, and this is a very, very important figure. On the x-axis is shear caused by gravity, V sub u g. We did not have the sub g, then we have sub g, and now 21.19, 3.18.19 or wherever, this has now become V sub u v for vertical. Anyway, I did not try to have consistent notation. I'm telling you, if you go through the various slide sets, the notation is not consistent because that would be pretty prohibitive undertaking. Anyway, on the x-axis is shear caused by gravity divided by the punching shear that concrete alone can carry, phi times V sub c. V sub c is the smallest value given by the three formulas that you have seen, typically 4 square root of f sub c prime in our units. Okay. So if you have 40% on the x-axis, that means the punching shear caused by gravity is 40% of what concrete can carry. On the y-axis is design story drift ratio. The design story drift, I think we went into yesterday. The deflection at the top of a story minus the deflection at the bottom of the same story under the design earthquake forces. Okay, the earthquake forces that are prescribed by ASCE 7 and BNBC 2020. Now, that is design story drift. When we say design story drift ratio, it is the design story drift divided by the story height. So when you have 0.2, that means design story drift is 2% of story height, which is the limit for standard occupancy buildings, you recall. Okay, so this solid line is very important. ACI 318 is saying you shall provide a prescribed amount of shear reinforcement, not at every slab column joint, as I initially said, but at slab column joints that are beyond this solid line, on this side of the solid line. Okay. Below, we do not need shear reinforcement. If you are on the solid line or above, you provide minimum shear reinforcement. Okay, so let us look at this. If your building is very stiff, design story drift ratio is less than 0.5%. Basically, nothing is going to happen. Okay, you don't have to worry about punching shear failure for a building that stiff. So your punching shear caused by gravity can be as high as 60%, 70% or more of what concrete can carry. Okay, no problem. Now, if punching shear caused by gravity is 40% of what concrete can carry, then if your building has a design story drift ratio of up to 1.5%, you don't have to worry about punching shear reinforcement. But if your design story drift ratio is above that, so 0.4 up to 1.5% story drift, no problem. But beyond that, you provide punching shear reinforcement. If your punching shear due to gravity is only 20% of what concrete can carry, then up to 2.5% story drift, you do not have to provide punching shear reinforcement. But if your design story drift exceeds that, then you provide punching shear reinforcement. Okay, so this is the SCI 31808 requirement. It's very, very important requirement. And if you provide this punching shear reinforcement, then you don't have to, I repeat, live with the limitation that punching shear due to gravity shall be within 40% of what concrete can carry. Now, these are details. Design story drift ratio shall be taken as the larger of the design story drift ratios of the adjacent stories and so forth. I will let you read this. The load factor on live load, this you have seen 100 times. It's unless you are designing a parking structure, a place of public assembly, or an area supporting more than 100 pounds per square foot of live load, the live load factor is 0.5. You don't have to use 1.0. Yeah, this is commentary. Provisions for shared reinforcement as slab column connections was added in 2005, and it tells you does not require the calculation of induced moments. Yeah, you can read it. There is in 31808 an option A, which has now gone away. It went away in 2011, which says that if you do a deformation compatibility check and show that everything is fine, you don't. Anyway, the option A under 21.13.6 is a bad option. It involves fudging of numbers, if you ask me. And although it is there in 31808, I would strongly advise you not to go there. That option has gone away, and for the right reason. That option we had to put in to get the whole thing approved. Some members insisted on a way out, and that provided a way out. And I don't want you to take a way out. Go by option B. Okay. Now columns. Members subject to bending and axial loads. Okay. So columns have axial load exceeding 1/10 S sub G F sub C prime. Dimensional limitations are shortest cross-sectional dimension, 12 inches. So a column of a special moment frame cannot have a dimension smaller than 12 inches. In many parts of the world, this is a how should I say, they cannot even conceive a column that big. They like 6-inch, 8-inch columns, and but this is a very necessary requirement. I think ACI has it exactly right. And anyway, so if it is a special moment frame column, minimum dimension is 12 inches. Ratio of shortest, so the long side to short side ratio cannot be any higher than 2.5. Long side to short side ratio cannot be any larger than 2.5. If you violate that limitation, if the longer side is more than 2.5 times the shorter side, does not mean that the member cannot be part of the seismic force resisting system. All it means is that it is not a column. It is now a wall and has to be designed as a wall. Okay. Strong column, weak beam requirement. It came up in discussion yesterday when there was a question about a tube. This is an extremely important requirement that has been with us since San Fernando, 73 UBC is when this was introduced. Now, first thing I want to point out is if it is a 3D frame, the strong column weak beam requirement will be checked on the plane of the screen and then perpendicular to the screen. Okay. So on the plane of the screen and perpendicular to the screen. And then unless everything is symmetric, side sway to the right will not be the same as side sway to the left. So we are talking about 4 different checks potentially. Be that as it may, the requirement is that the nominal moment strengths, we go with nominal these days. The combined nominal moment strengths of the columns meeting at a joint shall be at least 120% of the combined flexural strengths of the beams meeting at the same joint. The columns have to be stronger. The idea is if there is hinging, as there will be in the design earthquake, we design for that. The hinging should be in the beams, not in the columns. That is because beams are easier to repair than columns are. Columns are extremely difficult and expensive to repair. So we want the columns to remain elastic far into the earthquake excitation. If inelastic deformations need to develop, they should develop in the beams. Okay. The moment strengths are now at the faces of the joint. So moments at faces of joint corresponding to nominal flexural strengths of the columns and the girders. So in other words, we do the check in terms of nominal moment strengths at the faces of the joint. Okay, this is important because there was a time when we used to do that check with design moment strengths, and it used to be at the center line of the joint. Yeah. So nominal moment strengths and at the faces of the members. For columns, this is also important. So strong column, weak beam. The columns have to be stronger than the beams. So when we talk about column flexural strength, we would rather underestimate the column flexural strength. And we would rather overestimate the beam flexural strength. That would be conservative. Are you with me? Mm-hmm. So strong column, weak beam. We want the columns to be stronger than the beams. So when we calculate column flexural strength, we would rather underestimate it. And when we calculate beam flexural strength, we would rather overestimate it. So column flexural strength depends on the axial load sitting on the column. We have two seismic load combinations: additive load combination, counteractive load combination. Let us say the additive load combination gives you P sub U2 as the axial load on the column, and the counteractive gives you P sub U1. The moment strength corresponding to P sub U2 is M sub N2. The moment strength corresponding to P sub U1 is M sub N1. You shall use M sub N1 when you do your strong column weak beam check. The smaller of the two moments, you want to underestimate flexural strength of the column. Beams, you remember the effective flange width. The top reinforcement that sits in that effective flange width will contribute to the moment strength of the beam. And you must recognize that contribution, because remember, we want to overestimate flexural strength of the beam. If we underestimate the beam column flexural strength, overestimate the beam flexural strength. So do include the contribution of the slab top reinforcement within the effective depth to the moment strength of the beam. Okay, longitudinal reinforcement in columns. Minimum 1%, maximum 6%. The minimum 1%, I am sure I discussed in concrete design, becomes 0.5% because the limitation, like you can go with 1% of the required section, not the section when the column is larger than required, which it always is in the upper portions of a multi-story building. The 1% minimum can be based on the column section required rather than column section provided, except that you cannot go below 0.5% of the column section provided. Now that going down to 0.5% is not allowed for columns that are part of special moment frames. 1% is the absolute minimum reinforcement ratio. Okay. Now, starting with some edition of ACI 318, I don't remember which, Even for columns that are not part of the seismic force resisting system in design category D and above, we do not allow the reinforcement ratio to go down below 1%. Now, whether ACI 318 has that, I haven't checked. Anyway, for columns of special moment frames, which is what we are discussing, 1% is the absolute minimum, lowest. Okay. The upper limit of 6% is lower than the 8% that is allowed in the main body of the code. I think I remarked at that time, I will say it again, the 6% includes the lap splices, and that cuts it down to 3%. Initially you will have dowels out of the foundation, and then you will lap with the dowels. The 3% is way high. I discussed that. I remember 3% reinforcement in a column. You can place the reinforcement, but the problem, you have to think of the beam column joint, and let us try to visualize it. Okay, the beam column joint has the column bars going through. Okay, the column transverse reinforcement. Remember, every other bar laterally supported by a corner of a tie or a cross tie. That transverse reinforcement has to continue from the lower column into the upper column through the joint. That is not discontinued at the soffit of the beam. It goes through the joint. So visualize that. And then beam bars are passing through, top and bottom beam bars from left to right. And then another set of top and bottom beam bars are passing through from the beam that is going from front to back. Three-dimensional. We have beams running in two orthogonal directions. That is two sets of top and bottom bars passing through the column cage with the transverse reinforcement continuing through the joint. So with all of that, how are you going to place concrete inside the joint? So you are so much better off if the column reinforcement is light. Then you don't have so many legs of hooks and cross ties and so forth. Okay, so it is absolutely paramount that you understand that the column reinforcement has to be the lowest practicable. It is you cannot always have just 1%, but it is good to stick close to 1.5% to the extent that it is possible. I cannot overemphasize the need to keep column reinforcement light in high seismic construction. The spirally reinforced column, there are limitations on the pitch of the spiral and the volumetric ratio. Circular columns are very rare in buildings, so I will let you look at that. Nothing that I can add. As you go around the world, you will see that columns have typically a whole lot of longitudinal reinforcement, hardly any transverse reinforcement. This was a column in Mexico City after the 1985 earthquake. We looked at it. Low ratio of spiral reinforcement, very high ratio of longitudinal reinforcement. You see how the column has behaved in the earthquake. This one, I don't know if it is better, at least that the concrete has not, it looks a little better than the other one, but this is not a redeemable situation. This column has to be removed and replaced or whatever, So same thing, a lot of longitudinal steel, not enough transverse reinforcement. Okay, this figure I have shown you already. There is not a whole lot to add except something very important. Outside of the region of potential plastic hinging, which is defined here, the length shall be the largest of the larger plan dimension clear span divided by 6 or 450 millimeters. Okay. Outside of that, back before Northridge 1994, we used to revert to ordinary column spacing from chapter 7, which would have been 12, 14 inches. And then we saw, we had seen this before Northridge. We saw that in a big way at Northridge. Column failures took place, diagonal cracking starting where the special transverse reinforcement left off. So one of the first things we did after Northridge in 97 UBC is to say that nowhere along the height of a special moment frame column shall you have tie spacing exceeding 6 times the column dimension, not 6 times the longitudinal bar diameter, or 6 inches, whichever is the smaller of the two. Okay, so the spacing nowhere shall exceed 6 inches or 6 times longitudinal bar diameter, whichever is the smaller of the two. This again is a very, very good thing we have done, but this is pretty tough. I hope you understand. No more than 6-inch spacing anywhere along the height of a special moment frame column. Okay, this is as opposed to the 12, 14 inches we are used to. So okay, so this is detailing of special moment frame columns. This has been mentioned already. Every other bar laterally supported by a corner of a tie or a cross tie. The maximum distance center to center between any two supported bars 14 inches, and the clear spacing between a supported bar and an unsupported bar 6 inches. Okay. So there may be other details that I'm not thinking of. The S sub X in the spacing, I said it is between 4 and 6 inches, and that is given by this expression. The S sub X at one point has become S sub 0, I guess. I don't know. Anyhow, so, okay. Shear design of columns. Theoretically, we are supposed to do what we do for beams. Calculate the maximum shear by considering probable moment strength at each end of the column. Okay, so we can take a clockwise moment at the top, a clockwise moment at the bottom, divide by the span. Each case, it is the probable moment strength. Or we can take a counterclockwise at the top, counterclockwise at the bottom, divide by the length. Whichever gives us the largest shear is the column shear. Now the point is, we have strong column, weak beam. A column cannot develop a bending moment larger than what the beam brings onto the column. So because of strong column, weak beam, probable flexural strength of the column cannot develop except at the very bottom of the lowest level column. Okay, let me show you the next picture, and it will be clear what I'm talking about. The final item says member shear forces must not be less than those determined. So we will figure out the largest shear that can develop in a column, but you will not go below the shear that your analysis says develops in the column. I have never seen that to be a problem. We always calculate something larger. Okay. Now follow me closely here. So this is a beam column joint. This is the column below. This is the column above. This is the beam to the right. This is the beam to the left. Okay. The beam to the right has a probable moment strength M sub PR, R for right, and this is a negative moment as shown. Okay, equal and opposite moment acts on the joint. The left beam has a probable moment strength M sub PR, L for left, and if this moment is positive, that moment is, if that moment is negative, that moment is positive. Okay. So this joint is acted upon by M sub PR L positive to the left and M sub PR R negative to the right. So for equilibrium, those two moments added together divided by 2, if the upper column and the lower column are identical, would be the bending moment that would develop in the column. Okay, are you with me? So beam moments have to be equal to the column moments for equilibrium. So the sum of the beam moments have to be distributed between the upper column and the lower column depending upon their stiffnesses. If the stiffnesses are the same, then it is 1/2 to the upper column, 1/2 to the lower column. In any case, we can calculate the largest bending moment that can develop in the column. Okay? So the bending moment acting on the joint is M column. That same bending moment acts at the lower end of the upper column and at the upper end of the lower column. The upper column has the same moment acting at the upper end. We add the two moments together, divide by the height of the column. That gives us the column shear. Okay? Equal and opposite shear acts on the joint. So the point is that column shear calculation can be and almost all why almost always is based on the largest bending moment that can be developed at the column end, that can be brought onto the column end by the beams framing in. So we calculate the column shear not based on M sub PR acting at the end of the column, but based on the bending moment that can be generated at the column end by the beams framing into the column. Okay, I hope that is clear. Now, I have a number of pictures that shows you this is called the short column problem, short column failure. You see that every earthquake around the globe. This column was designed for shear from the central line of the upper floor to the central line of the lower floor, or maybe even clear column height. Let us give us the benefit of the doubt, clear column height. But then they build this parapet, cutting down on the column height. So now you are looking at enormously more shear. Shear is the moment strength at the two ends of the column divided by the height. If you cut down on the height by half, the shear is doubled. So that causes shear failure. As I said, this we see all over the place. This was after 94 Northridge. This was I forget the Kaiser, I forget the name of the building now. It had an L shape. That was a problem. But every joint, this was another building. The two different, but the same thing. The point is that this column was designed based on shear from the central line of this floor, this beam, to the central line of the lower beam. And then the actual height of the column is much shorter, which means much larger shear, and then you have diagonal shear cracks in both directions and failure. Okay. Now, columns supporting discontinued shear walls. I showed you this picture. There is no point in spending time on that. So if you have a column supporting discontinued shear wall, as in the picture, then the special transverse reinforcement, the transverse reinforcement that we would normally place within the plastic hinge regions at the column ends, shall be provided throughout the column height, not just at the two ends. And that reinforcement shall continue at least 12 inches into the footing. Or if the column sits on another structural member, the transverse reinforcement shall continue at least one development length of the largest longitudinal bar in that largest longitudinal column bar. Okay. So the main thing is, typically you are looking at it. So if you have a column supporting a discontinued shear wall, design category D, the special transverse reinforcement which you would normally place within the plastic hinge region only shall be provided throughout the height of the column and at least 12 inches into the footing. If you have an intermediate moment frame column supporting discontinued shear wall, your design category is C, not D. Same concept applies. Whatever you would have provided in the plastic hinge region shall be provided throughout the height. But the difference is, in the case of the special moment frame, the spacing is now 2.5 or 3 inches. In the case of the intermediate moment frame, the spacing required would be 8 or 9 inches. Okay, so it's the same principle, but obviously not the same reinforcement. So this is transverse reinforcement in an intermediate moment frame. We consider the same region of potential plastic hinging. Within that, we have to have closely spaced closed hoops. Okay. I forgot to tell you, special moment frames or intermediate moment frames does not matter. Outside of the plastic hinge region, those can be ties rather than hoops. They don't have to be closed by seismic hooks. Now, the spacing within the plastic hinge region is the smallest of those four. 8 times smallest longitudinal bar diameter, 24 times hoop diameter, 1/2 of the smaller plan dimension of the column, or 12 inches. We typically end up with 8 or 9 inch spacing of hoops in intermediate moment frames, as opposed to 2.5 or 3 inches in special moment frames. Outside of the potential plastic hinge region, we go with chapter 7 spacing, which would be 12, 14 inches. We don't have 6 bar diameter or 6 inches, whichever is the shorter of the two. And very, very importantly, no minimum cross-sectional area requirement on the transverse reinforcement. That is it. So the moment frame beam is not very different. Intermediate moment frame beam is not very different from the intermediate moment, the special moment frame beam, but the intermediate moment frame column is very, very different from the special moment frame column. Okay, beam column joint. I think this is the last thing. It's already 10:30. Anyway, I have no choice but to continue. and then we'll see what time it is. Okay. This is what I was talking about earlier. This is an exterior joint. The beam is terminating at the column. Okay. The hooked part development length from here to the end of the hook. The required hook part development length is in chapter 12, but this is being superseded by this requirement in chapter 21. You will go with this, not what is said in chapter 12. And the commentary says that this is, I don't remember now, 30 or 40% higher than what is required by chapter 12. And that is because these bars are subject to stress reversal. The bars that we are developing by hook are subject to stress reversal. Okay, so now hooked bar development length, and then it says, the text says, if you have top bars, remember top bars are bars that have at least 12 inches of concrete cast in one lift underneath the bar. If you are terminating straight top bars at an exterior joint, the required development length would be 3.5 times the hook bar development length. And if you're terminating other than top bars that are straight at an exterior joint, then the required development length of their straight bar shall be 2.5 times the hook bar development length. Typically, you will not have enough room, so you will end up with hooks or heads or plates or something. Okay, when beam bars are simply passing through an interior column, I don't know if you have ever thought about these things. This beam bar is in tension at this face of the column. The same bar is in compression at this face of the column. Here, it is negative bending moment. The positive reinforcement is in tension. Here, it is positive bending moment. The top bar is in compression. So the stress in the bar changes from compression to tension within the narrow confine of the column. And this transfer takes this change from compression stress to tension stress in the bar takes place through bond with the concrete. There is no other mechanism available. So that tells you that there is probability actually of considerable bond slip within the beam column joint. To minimize that bond slip, not to eliminate it, to eliminate the Committee on Joints, ACI 352, send us recommendations to 318 that this column dimension be 36 times the largest longitudinal bar diameter. That was absurd. ACI 318 said that would be the end of concrete construction. Who is going to construct columns that large? It's not economically feasible. So ACI 318 decided early on, and that has stuck through all these years. The minimum column dimension shall be 20 times the longitudinal bar diameter, largest longitudinal bar diameter. Okay. Lightweight concrete columns, I don't know how common they are. I think they're becoming, I don't know. I don't know about Bangladesh either. We had nothing, so we multiplied by the 20 by 1.3 and got the 26. That one is probably not important for you. Now when this condition is violated, you do not go for larger columns, you go for thinner bars. Okay, so the column dimension, this is interior column dimension, shall be no less than 20 times the largest longitudinal bar diameter. Okay, joint, beam column joint, effective area within the joint, A sub j. It is joint depth multiplied by effective joint width. Joint depth is the depth of the column as shown in the picture. The effective width of the joint is the same as the column width when the beam framing in is as wide as the column or wider. But when the beam framing in is narrower than the column as in the picture, the effective joint width is the smaller of two things, either the B plus the H, the beam width plus the joint depth, or B plus twice the shorter distance between the beam face and the column face. Okay, this distance is shorter than that distance, so this is X, shorter distance between beam face and column face. The effective width of the joint is less than or equal to B plus twice X. Okay, that would typically govern. And the effective joint width multiplied by the joint depth is A sub j, the effective area of the joint. Okay. Now, joint shear. The shear design of joints used to be like any other shear design. We used to say so much is carried by concrete, and whatever is not carried by concrete, you have to provide horizontal shear reinforcement to resist. That shear design was discontinued. I don't remember. I don't remember editions anymore. That was way early, 83. Anyway, quite some time ago. Based on Jim Jirsa's research, we said that that is not the way to go. The fact of the matter is, when you provide transverse reinforcement within a joint, the shear strength goes up, but only up to a point, not beyond a point. If you keep on adding transverse reinforcement, the shear strength at one point levels off. You keep on adding transverse reinforcement, the shear strength of the joint simply doesn't go up anymore. So in view of that finding, the joint design of ACI 318 says you shall continue through the beam column joint the column end transverse reinforcement. As I already said, you shall not discontinue that at the soffit of the beam. You will continue it through the beam column joint. And as long as you have provided that prescribed amount of reinforcement, transverse reinforcement within the joint, your joint is good for so much shear strength. Okay. Adding more transverse reinforcement will not do you any good. So so let us look at where joint shear comes from. So shear here will be this tension force, the tension in the top reinforcement of the right beam. And you can see that we have taken the stress at 125% of F sub y. This is based on probable strength. So shear here is the tension in the top reinforcement of the right beam. It is all that compression at the top of the left beam. But all that compression in the concrete and in the reinforcement is equal to the tension in the bottom reinforcement of the left beam. For equilibrium, the compression has to be equal to the tension. So the shear here is the tension in the top reinforcement of the right beam plus the tension in the bottom reinforcement of the left beam minus the column shear. And the column shear, you know how to calculate based on column end moments. Okay. So that shear cannot exceed phi times V sub n, the shear carrying capacity of the joint. The joint is good for so much. If it is an interior joint, it says confined on 4 faces, 3 faces, etc. And I will tell you what confined means. But basically, if it is an interior joint, your nominal shear strength is 20 square root of F sub C prime times A sub J in our units. If it is a joint confined on 3 faces or 2 opposite faces, these are joints, exterior non-corner joints. Then you have 15 square root of F sub C prime. And corner joints, you have 12 square root of f sub c prime, 20, 15, and 12. Now, this says that confined means beams framing into all four faces of a column, with each beam wide enough to cover 3/4 of the column face. I will repeat all this verbiage here tells you that a confined joint means beams framing into all four faces of the joint, with each beam wide enough to cover 3/4 of the column face. If you have a confined joint, you need not continue 100% of the column end transverse reinforcement. You are allowed to continue only 50%. Okay, so that is, and most people I know, they do not vary the spacing of the transverse reinforcement. They drop the sum of the cross ties, making concrete placement within the joint much easier. Okay. So that is a detail. I'm not sure I put it on the slide, but that is kind of important. Okay, interior joint failure. Some well, this is after Northridge. This is pre-1973 UBC construction. This is worth looking at, the difference. Back in those days, the joint was not paid any attention to. So this was a Kaiser Permanente facility. Kaiser Permanente is a healthcare system, very big in parts of the country, including the West. Anyway, you see the two floors have come together. This was the beam of the upper floor. This is the beam of the lower floor, and the column separating the two is hanging out here. Okay, and that's because the joints have failed completely. And the joints have failed because there was no transverse reinforcement in the joints, so nothing to speak of. There may have been a tie or two with 90-degree hooks, nothing that makes any difference. Okay, so this again you see after every earthquake in older construction. Okay, last topic, joints of intermediate moment frames. There isn't much of a requirement up until 31819 has changed everything, but that's in the future for you. Okay, when gravity load, wind, earthquake, or other lateral forces cause transfer of moment at. So what it is saying is, you remember the moment transfer from slab to the column. That moment in the column will cause column shear, and that shear has to be designed for. And then the only requirement is that in the intermediate moment frame joint, you will have minimum shear reinforcement as given by this expression. The minimum is given by that, except that it shall not be less than that. So this we discussed in our shear design session. So the minimum shear reinforcement that is required in beams as well as columns, in this case we are talking about columns, must be provided in the joint of an intermediate moment frame joint. So the basically, those are not basically, those are the only two requirements. You shall provide for the shear due to moment transfer, and you shall provide within the intermediate moment frame joint minimum shear reinforcement as required by the code. The only other thing that is said, this is not necessarily joint, the language is connection. At connections of principal framing members, which would obviously include joints. Enclosure shall be provided for splices of continuing reinforcement and for anchorage of reinforcement terminating in such connections. So add connections of principal framing elements such as beams and columns. Enclosure shall be provided for splices of continuing reinforcement and for anchorage of reinforcement terminating in such connections. Okay, anchors have to be enclosed. What was the language? Enclosure. Yeah, shall be enclosed, and the anchors have to be enclosed. Then it says enclosure shall consist of external concrete or internal closed tie spirals and stirrups. So I don't know that it adds anything to what you already know, but this is a basic non-seismic requirement that I wanted to mention to you. Okay, I have two more slides, one and the one I want to end with. NIST, National Institute of Standards and Technology, publishes these so-called tech briefs, technical brief. These are 40-page documents on very specialized topics, and these are excellent documents that gives you a very good overview of the topic. The first one was on seismic design of reinforced concrete special moment frames. As you see, this has now gone through how should I say, update. Anyway, these are available on the internet totally free of charge. If you would Google NIST Tech Brief, you will see by now there are, it's approaching 20 by now. I forget, 16, 17, something like that. All of them are available to you free of charge, and I would strongly urge you to get hold of this and take a look. The final slide. This was a parking structure at Cal State Northridge, California State University Northridge, after the 94 earthquake. This special moment frame, this was a very interestingly constructed moment frame, but I wouldn't go into that, time is short. This special moment frame was part of the seismic force resisting system. So this is a special moment frame. When we detail a special moment frame, we detail it to sustain inelastic deformations in its own plane. Okay, in the case of this frame, the frame should have been capable of withstanding deformations in the left to right direction or right to left direction. Here in the earthquake, for reasons I wouldn't go into, the special moment frames have undergone out of plane displacements of several feet. And look at the frame. You know, it has cracked, but that's about all that has happened. Nothing, no piece has flown, not the frame is in, I don't want to say in good shape, but it definitely, the frame itself has held together admirably. So all these rules that we went over, that are the result of learning from many earthquake experiences. I can assure you that they give you structures that perform. I mean, there is a huge difference between pre-1973 concrete and the concrete we are building today. It's incredible difference. And I personally have absolute confidence in what we are building today, provided you comply with the code. That is a big thing. You have to be in compliance with the code. All these rules have been placed in there for reasons. and you cannot just ignore them. Okay. Yeah, thank you very much. I'm sorry about the time. I didn't expect to go over today. Anyway, we have 10 minutes of regulation time. I'll be willing to stay beyond. So let's have questions.
Thanks, Dr. Ghosh. So today, actually, we have a lot of questions, and I was unable to get to them because there was an issue with yesterday's quiz that I had to fix instantly,
Okay.
and I was doing that. So yeah, yesterday the quizzes like there was a problem with submission. I have fixed that issue. So if you go back and submit the quiz, it will submit now. Yeah. So let's go. We don't have a lot of time, Dr. Ghosh, so
No,
let's
I know.
just go over. Uh,
Let's do what we can.
yeah, yeah, yeah. So I'll go from the top. So in a column which has rectangular hoops at a vertical distance of 5 inches, should be 6, right? Is the vertical spacing also applicable for cross ties, which are 90-degree hooks? Or can we place these cross ties alternatively at a spacing of 10 inches?
Absolutely not. The cross tie doesn't have a separate existence, not in a column. Okay, so the whole thing, the hoop all around and the two sets of cross ties in two orthogonal directions gives you one unit of transverse reinforcement. And the spacing applies to that unit of transverse reinforcement. So the spacing, whether it's 5 inches or 4 or 3 or whatever, is for this entire ensemble of one hoop all around and two sets of cross ties into orthogonal directions. There is absolutely no room for the cross ties to be placed apart from the hoops, and no, that it doesn't work that way. Absolutely not. No.
Okay, a few other questions again. Dr. Ghosh covered it in his presentation.
Only time we have discrete cross ties are through the web of shear walls. The longitudinal reinforcement in the web of a shear wall, uh, how should I say, to go with the longitudinal reinforcement in the web of a shear wall, we have transverse reinforcement. And through these, there are typically two layers of these vertical bars and horizontal bars in the web of a shear wall. Through the two layers, we quite often would install cross ties. Those would be just the cross ties, and that spacing is something like 12 inches. There is nothing specified in the code, but other than that, I do not know of just cross ties being used for transverse reinforcement.
Okay, so ties and columns are used for both confinement and to resist shear. Is it not contradictory that we use 100 KSI? We can use 100 KSI for confinement and 60 KSI for shear reinforcement, where both are same.
It's not contradictory at all. It's a question of what value you use in calculation. Okay, so transverse reinforcement, the confinement reinforcement, how much you need is given by those formulas that I have been pointing out, giving you minimum cross-sectional area. Are you, do I need to go back? I don't know. Uh, okay, here. No, here. Okay, so when we are talking about confinement, we are talking about this. And so minimum cross-sectional area must be the larger of the values given by the two formulas. This f sub yt can be up to 100 ksi. When you figure out the shear reinforcement required, I obviously don't have shear. We discussed the shear design module of the concrete courses. There you use the yield strength of the shear reinforcement, and there you will not go beyond 60 ksi. That's all. There is no contradiction. No contradiction. It happens to be the same piece of reinforcement. It serves two purposes. When we try to figure out is it sufficient for one purpose, we use f sub yt of up to 100 ksi. When we try to figure out is it sufficient for the other purpose, we use f sub yt of 60 ksi. There is no contradiction that I see.
Okay. Is there any limitation on beam depth? I mean, is there any minimum depth of beam of which can I provide a beam of which has a depth equal to slab thickness? Is it permitted?
Read the whole thing again.
Is there any limitation on beam depth? And can I provide a beam with the depth equal to slab thickness?
If you provide a beam equal to slab thickness, then you have a flat plate. You don't have a beam. Okay. There is no. Is there a minimum depth? Let me. There is no explicit minimum depth, but I want to go to the here. Okay, so width to depth ratio of the beam is larger than or equal to 0.3. Does that tell you anything? Or so the other way around, the depth of the beam has to be no more than 3.33 times the width. Okay, that doesn't give you a minimum. Yeah, I do not know what to tell you. There is no minimum. If you want the beam not to stick down below the slab, you don't have a beam. You have a flat plate, and that I'm sure of. Okay. Now, can you just stick out a couple inches? I wouldn't do it. It is not not the code cannot be explicit about everything. But when we say beam column frame, we mean an actual beam that a very shallow beam. I don't know. How is a 5-inch deep beam going to act as a beam? Well, where does the moment capacity comes from? The effective depth is very shallow. So I do not exactly know what you are thinking of. No, there is no explicit lower limit on the depth. But if you ask me, it has to be a good faith beam, not something you are trying to manipulate your way into. So
Will there be a session on base isolation? I don't think so, right?
no.
Seismic analysis. What are the effective remedial actions to prevent short column failure of RCC building?
Read that again.
What are the effective remedial actions to prevent short column failure of RCC building?
That's if you're talking about existing buildings, I do not know. Uh, that will have to depend on that will have to be case by case. If you're talking about a new building, it is very, very simple. You have to figure out the actual height of the column in service. So it is the actual clear height of the column that will govern the shear that develops in the column. Okay. If you have an existing building dating God knows when, there is no general thing that anyone can tell you, not just me. You will have to deal with it existing buildings have to be dealt with on a case by case basis. You have to take a look, see what you have, and then see what you can realistically do. Sometimes there isn't anything you can realistically do other than raising the building. That does happen. So
Okay. And this is again covered, but yeah, but I think that you can give a short reply. In addition to provision of ACI 21.13.6, I repeat, ACI 21.13.6
hmm.
is for SDC D, E, or F, but you mentioned that it is for IMF. Are there any reasons? Also, slabs without beams is not permitted in SDC D. Then why ACI 21.13.6 refers this under SDCD?
Okay, the second question is much easier. Okay, when I said repeatedly flat plate column frames are not allowed in seismic design category D buildings, I always say it as part of the seismic force resisting system. They cannot be part of the seismic force resisting system. Does not mean they cannot be used in design category D buildings. They are used all the time. And I also mentioned they are used in conjunction with 100% lateral force resisting shear walls, or sometimes it could be steel brace frames. Okay, so it is not that flat plate column frames cannot be used in design category D buildings. I never said that. Nobody has ever said that. They cannot be used as part of the seismic force resisting system, which means the seismic forces have to be taken by something else. That something else in concrete buildings is shear walls. So we built all over the place flat plate column frames carrying gravity only, 100% lateral force resisting shear walls. And this is where deformation compatibility comes in. This is where 21.13.6 comes in. Are you going to satisfy deformation compatibility requirement, which is difficult to do? Or we said if you are not going to check, throw in punching shear reinforcement. This is why it is placed in 21.13.6. That is the right section, gravity frame section. Okay, and then when we had to figure out what to do with intermediate moment frames, okay, the logical thing is keep the gravity punching shear low, keep it below the punching shear caused by gravity, keep it below 40% of what concrete can carry. But then there was an outcry. I mean, we cannot build them. This is prohibitive. So then 318 figured out that we have provided this in 21.13.6, this throw in punching shear reinforcement at joints that required them. 21.3 happened to reference 21.13.6. Okay, so that 21.13.6 was already available, and it looked like a very attractive alternative to living with a limit that was very, very stringent. So, but I emphasize, I never said that flat plate column frames cannot be used in design category D. No, they cannot be used as part of the seismic force resisting system. There is a huge difference between the two statements.
Okay, there's a question related to, I think this I answered already. So skip this. Buffering issues. You have buffering issues. Not. Yeah, if you have attended the session, you won't have a problem. So, okay. In ACI handbooks, flat plate example, there is a minimum unbalanced moment function of dead load and live load at subsequent panels. That is added with the 1.D plus 1.6L for punching shear calculation. We don't see it in your slides. Do we need that? Dr. Ghose,
I
are you aware of
you,
anything like that?
you have to read the whole thing.
In ACI handbooks, flat plate example,
Mm.
there is a minimum unbalanced moment, which is a function of dead load and live load at subsequent panels. That is used for punching shear calculation. But we don't see it in your slides.
I don't understand it. I mean, when we did so, if it is a slab subject to gravity loading only, then the gravity loads that will cause bending moments are there are two load combinations 1.6D or 1.4 dead plus 1.7 live. Okay. And we did exactly that. If you look through the punching shear design example that we did, that those were the load combinations we considered, unless my memory is failing me completely. That was those were the load combinations considered. So when you say you don't see those in my whatever, I don't quite understand. But I will go further. When you bring wind or earthquakes into the picture, in let's say earthquakes, then the load combinations that you have to consider are 1.2 dead, 1.6 live, 1.2 dead, zero point 0.5 live, in our case 0.2 snow, and 1.0 E, or 0.9 dead plus 1.0 E. Those are your load combinations. The shear will come from the additive load combination 1.2 dead, 0.5 live, zero point 0.2 snow. Okay, so that and 1.0 earthquake, that is big seismic. So the shear that you have to design for will come from that load combination. And I don't think the ACI examples show anything different than what I have shown in the examples that were part of. You remember we did flexural design of flat plates one day, shear design of flat plates one day. It was the same example both days, and in that you will see that the two load combinations, 1.6D or 1.4D, or whatever. You see what I'm saying. Yeah.
Okay, so the last question we'll take today. I mean, there are a lot of questions, but yeah,
Mm,
we've already passed time.
mm.
Um, Let me see. Is it allowed to have an SMRF building we where we can this okay, let me rephrase. For architectural purposes, we sometimes cannot provide beams in every column to column line. Is it allowed in an SMRF building?
Read that again.
For architectural purposes, we
Hmm.
sometimes cannot provide beams in every column-to-column line. Is it allowed in an SMRF structure?
So if you don't have beams between some columns, so those I don't know, without drawing picture is very difficult to explain. Your frame, your special moment frame will consist of the beams that you have and the columns that you have. So let us say you have 4 stories and 5 bays. Okay, and let us say in the at the top, in the middle bay, you don't have a beam. Okay? So then your frame, the frame you're designing as part of the seismic force resisting system will be minus that beam. And then you are okay. What you have, what you don't have, if you don't count on it, you are all right. Now the problem is that if too many beams are missing, and you end up with columns that are 2 stories tall, that is a problem. But I don't think you are talking about no beam. Having no beams doesn't mean that you have nothing. You probably have the slab and no beam sticking out. So in that case, the slenderness may not be a problem. So what I said is what I will say, that if you don't count on those beams as part of your seismic force resisting system, the missing beams, you should be okay. This is a general answer without looking at exactly what you have in mind. It's difficult to come up with a better answer, but nothing forces you to have beams between the columns at every column line. That is not required. No, that is not that is not the intent.
Okay, Dr. Ghosh. So I think, yeah, we will end today's session here. It's already 15 minutes past 11.
Yeah,
And the next session will be next Monday, right?
yeah,
Uh,
yeah, yeah.
so that will be on share walls, I guess.
Shear wall detailing.
Yeah, share wall detail.
Yeah, but Saturday, Sunday there are sessions. I don't remember what they are.
I think geotechnicals.
Yeah.
So Saturday and Sunday we have geotechnical sessions.
Okay. Okay. Dr. Abidin. Yeah, you have questions waiting for him.
Okay. So thank you again, Dr. Ghosh, for this amazing presentation. It
Thank you.
was it was I know that you have taken a lot of effort preparing this. And once again, I apologize for the quiz submission. That was the problem that was happening. So that has been fixed. I don't. I think in the future that won't happen again. So that I fixed. And I will open up the quiz in a couple of minutes for this session. And and like just wishing to see you again on Saturday and Sunday. Thank you so much.
Yeah. Thanks a lot, buddy.